Alright, so this is a walkthrough of the El Mundo challenge from the Hack the Box CTF, Hack the Boo 2024. Um, just get into it, I guess. So these are the files that are given to you. You get Python solve script, uh, the glibc binaries, or sorry, there you go. You got the libc and the linker, and then the actual binary. So let's see what kind of file the binary is. It's not stripped, so debugging symbols are still there. It's a standard Linux executable. If we go ahead and run that, we can see it's printing out some cool information for us. Oops, delete that real quick. So it shows you the stack frame layout. Right here we have the return address for the current function we're in, base pointer, local variables, and then I guess the buffer that we're reading into. Yeah, okay. So start of the buffer. This is where we're inputting our code. Here we have some local variables, yada yada yada, and then the return address. So from here we could kind of see that it's going to be 64 bytes from the beginning of our buffer up until the end of the return address. So it says overflow the buffer, overwrite the local variable with junk, overwrite the save REP with junk, overwrite return address with the address of the read flag function, and it gives you the address right here. Okay, so the solve script they gave us, it's already set up with some stuff, so uh, we can see it's using Pwn tools here. Oh, what's my vim doing? Okay, we're using Pwn tools here. We're loading in the binary as an object, so we can do some cool function stuff with it. Right here, we're gonna change this to true so we can test our solve locally before running it. And then some cool stuff. All right, so if it's local, it's gonna start the process locally. If it's not, it's gonna connect to the server. And then here it's loading the binary itself as an object, so we can index things from it. That's if you're more interested in that, you can look at PwnTools documentation. It allows us to do cool things like um, pull out function addresses and whatnot on the fly. But right here you can see it says change these. So n bytes. If we look back at what the program's doing, somewhere it said n bytes. Okay, n bytes read receives. Alright, not entirely sure what that's asking, but I loaded the binary into Ghidra, so we have a decompilation of it. So we can see right here, we're getting a read onto our buffer on the stack, and obviously our buffer's not 256 bytes long, it's 32 as we were told. So we get to overwrite past the point of the buffer. So if we supply more than 32 bytes, it's going to keep writing and writing and writing, and eventually it's going to get all the way up to 256 bytes. So our return address is within that range, so we can reach it and overwrite it. So you can kind of figure out that the return address, like to override it, the distance. So it's literally pointing at the stack here. Normally you'd hop into a debugger and print the stack or look at the stack or whatever to see how you can reach the return address. But right here, they're basically handing it to you. So right here it has 64 bytes. That's not correct. If you were to write 64 bytes, it would be filling the return address. So just to show that, oops, just click 64. If we input that here, we can see that the return address did get overwritten with some of those that cyclic pattern that we gave. So each one of these is worth 8 bytes. You can just see that here. This is a byte. It's also like the hex for the character we input. So lower A. So this is that filling it up. So we have 8 bytes here. So if we wanted to reach all the way up to the return address but not overwrite the return address, we would do 1, 2, 3, 4, 5, 6, 7. So we would do 7 times 8 bytes, or 56. I'll write that here, 7 times 8. So when we go in and we write that, we write all the way up to the return address, and I'll show that again when we run the binary. So here you can see we overwrit the saved REP, and we actually overwrit a byte of the return address because of the uh, when we hit enter, it also sends like a new line character. So that's what this is right here. So that's why the program is still segmentation faulting. But now we can input the address of the read flag thing here, and I'll show you how we can do that with Pwn tools. Oh, sorry. So we go down here. This is what they currently have. I don't know if this is actually the right address, but we can take this object that they gave us right here, the ELF. We can say e.symbol, and then we'll say read underscore flag. So what that'll do is that will pull out the flag symbol for us. So I'll log that for us so we can see what the actual address is when we run the script. Yeah, cool. That's the solver. So now, in theory, what should happen is we should overwrite all of these bytes, and then when we get to the return address, it will be the address of the read flag. When the function returns, instead of returning to whatever it was supposed to, it will jump to that function. So instead of returning from main, I think normally it returns a libc star main, but instead of doing that, it will actually jump to the read flag function, and then it will open the flag and write it to standard out. So we can test that here locally. Oh, should probably fix that. Oh my, what did I just do? All right, hold on. I'm breaking my tmux, or sorry, my vim. Okay, there we go. And it broke. Nice. Why did it do that? Oh, okay. Yeah, okay. I need to change this. It never actually changed. So yep, it's running locally. It's going to use the binary instead of trying to connect. We run the solver and boom, we got the flag. So cool. That is how you solve this challenge.